Hello there. I'm going to be doing a video on chapter 4.3 from our book. This is the first video from this chapter, and the chapter information is on maxima and minima. So there's a few definitions that you see on the screen right now. They are from the book. I've cut and pasted them out of the PDF that we had, or sort of. It was more involved, but anyway. Um, so let's talk about the two basic types of maxima or minima. So our first definition, let f be defined, a function defined over the interval I, and let some value c, so c is going to be an x value, be in I. We say that f has an absolute maximum on I at c if our function at c is greater than or equal to every other function of x. All right, so whatever the domain is. So essentially what that's saying is your y value at c is at least equal to, if not bigger than, your y value at every other point in your domain of 4x. Okay, and again, for all x and I, meaning, so all x and I is this here, and what that simply means is that x is in the interval that you've designated. And the same thing works for absolute minimum. So an absolute minimum is your y value at that value, at the x value c, is going to be smaller than or equal to any other y value in your interval. So if it's got one of these things, we say that our function f has an absolute extremum on I at the value c. So typically we're not looking for the y value specifically, we're looking for the x value where there's a max or where there's a min. All right, the second definition that they give us, or this one's a theorem, excuse me. So theorem 4.1 is the extreme value theorem. So if we have, and this is very important, if f is a continuous function over a closed interval and bounded interval, then there's a point in that interval at which f has an absolute maximum, and there's a point at which f is an absolute minimum. So let's talk about what closed simply means, the closed brackets, which means we're going to have a lower value and an upper value, and those values are going to be included. Continuous, we know what continuous is. We've done the definition of that. Essentially, no breaks, no holes along that interval from a, our lower value of x, to b, our upper value of x. Okay. Now bounded. So what does bounded mean? So bounded simply means that there's a top and there's a bottom. So we don't have some sort of asymptote within, at one end or the other of our interval where something's going up to infinity, okay, or down to negative infinity for that matter. So there's a bound. There's an upper level for y and there's a lower level for y. So say y can't be above the number 8, or y can't be below the number 6, or something like that. And finally, our last definition there is a function f has a local maximum at some value c, which is an x value, if there exists an open interval I containing c such that I is contained in the domain, so I has to be in the domain of our function f, and f of c is greater than or equal to f of x for all x in that interval. So what this means is essentially we're going to be looking for something like a peak or a valley. Open interval means, again, you don't have to include the numbers around it. So essentially, if you make a very, very smaller and smaller and smaller interval around it, it's always going to be at the top for a maximum or at the bottom for a minimum. All right, so I'm going to scroll down and take a look at a couple problems from your book. Okay, these problems are from 4.3. They are on page, let's write this down here. All right, so these are on page 376. Okay, let's take a look at number 100. So first of all, our instructions. For the following exercises, determine whether the local and absolute maxima and minima occur on the graph given. Assume domains are closed intervals. Assume domains are closed intervals unless otherwise specified. So we're going to assume that these are all closed intervals. So let's take a look at our interval for problem number 100. Let's see. So it looks like maybe around here. And it looks like it does go to 3. So our interval, our x values, can take anything from just shy of -4, or just above -4, I should say, to +3. Okay, so we're looking for the maxima and minima on here, and we want to determine whether or not they're local or absolute. All right, so let's look for uh, our absolute max and min. We've got a closed interval here. We appear to have a bounded interval. We're cutting it off at 60 on top, and it looks like -40 on the bottom, so that's our bound. So if you note, this is our upper level, and this is our lower level. So we're bounded. We have a closed interval. Our interval is, I'm not sure where it begins, but it looks like it ends at 3. And we just say it begins at -4, I suppose. Maybe it does. Okay, so we're looking for the extreme values, where the extreme values for y, remember, are here and here. All right, so we have an absolute max at we'll call it -4. I don't know if it's -4 or not. We're going to call it -4. Remember, this is the x value. Okay, we see the y value is 60, but the x value is where our absolute max is. So we can put it as a points. -4 and 60 is the points of interest there. All right, and then we have an absolute minimum. And that looks to be at -3. So it looks like it's the points -3 and -40. Okay, so now local max or mins, and I've done a little sort of coloring on this that has kind of impeded the view of the right part of our graph, but it looks like, here, let me see if I can get rid of this. I don't want to try. I may delete the whole thing. That would be bad. All right, so we can point out local maximum. There's a local maximum up here, and there looks to be a local. It looks like the slope is kind of coming down, but it doesn't look like it hits bottom until 2 down there. Okay, so it looks like we have a local max, and that's not quite what I wanted, but we're going to do it. We're going to do it it's at the points -1. And I'm not sure what the y value is on that, neighborhood of 10. So uh, that's fine. And it looks here like the local minimum is at 2. And it looks like the point is at 2, 0. So it looks like that's where we're at for this particular one. So let's take a look at problem number 101 here. All right, so I don't know what our domain here is. I'm gonna write a domain down of what I think it might be. All right, so it looks like the domain goes from, I don't know, negative 2. I don't know if it's 2.5 or what. We'll call it 2.3. I don't know. Negative 2.3, and I'm gonna say 3 is the end here. So that's our interval. Okay. So we have a local max up here, or well, I guess an extreme max. So that's an extreme maximum, and this is an extreme minimum. So we have extreme max or absolute. So absolute max is at, looks like at the end, so negative 2.3. And absolute min is, we're going to call it at 3, the x value of 3. Okay, so we're looking for local max and min now. So we have a local min here. We have a local max here. I don't see any points connecting -1 and 1 where we might have a max. I don't know if it's horizontal anywhere or not. I can't really tell, so I'm not going with it. And we have a local max there at 2. So local min looks like we have a point x equals -2 and x equals 1, and local max is going to be at -1, so x equals -1 and x equals 2. So what would we do if we had a horizontal line and say just a horizontal line? Let's scroll down and just create something. Say we had the line here. Say f of x equals 2 on the interval. Let's make an interval. So on the interval, say -5 to 5. So what do we do with this? Well, any point on this interval is going to be larger than all the other points on the interval. So essentially what we have is we have absolute max on every point in the interval, or we'll just say x within the interval. And the same thing for the absolute min. Any value on the interval is also going to be smaller than all others. So So that's kind of an odd case, but that's how you could look at a straight line. It fits our definitions just fine. And that is video 1 of this chapter.